Imagine it is late October 2025. You are standing right in the middle of Delhi, and you cannot even see the buildings at the end of the street.
Yeah, that thick gray soup of urban smog.
Exactly. It burns your eyes, it catches in your throat. And right at the peak of this major public health crisis, as millions of people are literally choking on the air, the government looks up at that toxic sky and decides to try something that feels, well, straight out of science fiction.
Right, they then decide to engineer the weather.
Yes. The plan was to fly a plane directly into the smog, hit a button, and artificially trigger a massive downpour to just, wash the pollution away. And that is exactly what we are unpacking in our deep dive today. We are looking at the strategic reality of cloud seeding.
Which is such a critical topic right now.
Yeah.
Because this isn't just some niche science experiment anymore. By 2025, this would become a central, highly publicized talking point in national discussions around urban air pollution, water stress, and really overall climate resilience.
Right. And our mission for this session is to give you a complete structured understanding of this topic. We are going to look at the science, the actual facts from that 2025 pilot trial in India, and the strategic policy implications.
Think of this as your high-scoring answer preparation system. By the time we finish, you will have a mental cheat sheet for this issue. Background, facts, government rationale, and a critical evaluation.
Perfect. So let's start with the background layer. Before we evaluate whether this technology can solve our pollution crises, we have to understand the mechanics. How do you actually seed a cloud?
Well, to understand the mechanics, you first have to realize that they are incredibly stubborn. A cloud is essentially just a massive collection of microscopic water droplets or ice crystals floating in the air.
Right, but they are too light to fall, right?
Exactly. They are so small that the atmospheric updrafts just keep them suspended up there. They will not fall as rain until they grow heavy enough to overcome those updrafts. Gravity needs to be able to pull them down.
So the goal isn't creating water out of thin air. It's chicking the water that is already up there into getting heavier.
You hit the nail on the head. And that is where the seeding agents come into play. We are talking about dispersing specific chemicals, typically things like silver iodide, potassium iodide, or even just simple sodium chloride, which is salt.
And how do they get those chemicals up there?
You can use rockets, ground-based generators, or, as is common in large urban operations aircraft and helicopters, they shoot these agents directly into a target cloud.
Okay, I was trying to visualize how a dusting of salt or silver iodide suddenly triggers a downpour. Kind of makes me think of a crowded, chaotic room.
Oh, I like where this is going.
Right. Imagine a massive convention hall where thousands of people are just walking around aimlessly, never really interacting. That is your water vapor.
Go ahead, yeah.
Then if you drop a major celebrity right in the middle of that room, that is your silver iodide, suddenly everyone starts clustering around them. The crowd gets denser, heavier, and completely anchored to that one spot.
That is a brilliant way to conceptualize what atmospheric scientists call coalescence. You are introducing a nucleus, an anchor, right?
A magnetic core, basically.
Exactly. Either a cloud condensation nucleus or an ice nucleus. And it forces that scattered moisture to coalesce, to merge and grow. And to build on your analogy, the type of celebrity you drop into the room completely depends on the temperature of the room.
Wait, so the chemistry changes based on the cloud's temperature?
Oh, absolutely.
Yeah.
The chemistry has to match the thermodynamics. And this gives us the two key types of seeding you absolutely need to remember for your notes. First, we have hygroscopic cloud seeding.
Hygroscopic. Okay, what does that involve?
This is for warmer climates. It is specifically used for warm, liquid clouds, the kind you typically see in tropical regions or during summer monsoons. Here, the agent of choice is salt, sodium chloride, or potassium chloride.
Because salt naturally absorbs moisture, right? It
Yep.
just pulls the water toward it.
Yes, very aggressively. The salt particles act as giant condensation nuclei, accelerating that coalescence process so the liquid droplets merge and fall faster. But if you move to colder altitudes, you need the second method,
Which is?
glaciogenic cloud seeding. This is for supercooled clouds.
Super cooled, meaning the water is below freezing but not ice.
Exactly. It's below freezing but still in a liquid state because it lacks a nucleus to freeze around. Needs a trigger. And that is where silver iodide comes in.
Ah, so the silver iodide acts as the trigger.
Right. The molecular structure of silver iodide is remarkably similar to the crystalline structure of natural ice. When you spray it into a supercooled cloud, The water droplets are tricked into freezing onto those particles.
Oh, wow. So they form ice crystals, gain mass, and then just fall.
Precisely. They fall, and they either melt into rain if the lower atmosphere is warm, or they fall as snow if it stays cold.
Okay, so that is our memory layer for the science. Hygroscopic uses salt for warm clouds, and glaciogenic uses silver iodide for cold clouds. But, and this is a big but, atmospheric theory is completely different from the chaotic airspace over megacity.
Oh, without a doubt.
Which brings us to the actual test case. Let's pivot to the real-world application, the highly publicized 2025 pilot project in Delhi.
Right. This was a major trigger event for environmental policy in the region.
And we need to lock down the facts and data here. These are the memory anchors you need to highlight. The Delhi government approved this pilot with a budget of 3.21 crore rupees.
Yeah, 3.21 crore. And it was a massive display of interagency coordination. You had meteorological agencies, aviation authorities, and academic institutions all working together.
Specifically, it was the Indian Institute of Technology, IIT Kanpur, managing the hardware. They used a specially equipped Cessna 206H aircraft registration VTIAT, if you want to be incredibly specific.
And that ties right into the whole Atmanirbhar Bharat relevance, right? Indigenous institutions stepping up for complex technological deployments.
Exactly. It is a great example to quote. So they had the plane, they had the silver iodide and sodium chloride flares, but the timeline is where things start to get, well, problematic.
Extremely problematic.
The original plan was to do this in July. July is monsoon season, lots of wet clouds, but it got delayed over and over, and the flights didn't actually happen until October 28th, 2025.
And that delay completely changed the operational reality. Because by late October, the meteorological profile over Delhi had shifted entirely.
Which brings us to the most glaring data point in this whole case study. For cloud seeding to work, for that coalescence to happen, the target clouds need a moisture content of around 50 to 60%.
Right. You need water in the cloud to make rain.
But on October 28th, the clouds over Delhi only had 10 to 20% moisture.
Which is effectively a dry cloud.
So I have to push back here. If the science says you need 50% moisture, and the data showed they only had 10 to 20%, why did they even fly?
That is the crucial governance question. Why push the button? It really highlights the tension between institutional pressure and scientific reality. When you have allocated 3.21 crore rupees, and the public is quite literally choking on toxic air, the administrative imperative to show action is overwhelming.
So it was basically a high-tech PR move at that point.
I wouldn't call it purely PR, but there was certainly a need to prove the capability. And from an operational perspective, the official reports did call it a success.
Wait, a success? How?
Well, the interagency coordination worked. They got the Cessna cleared through highly restricted airspace, the flight planning was flawless, and the flare deployments triggered perfectly. They proved they had the logistical capacity.
Okay, sure, the plane flew. But meteorologically it failed. Because the sky was dry, they only recorded a microscopic trace of rain around 0.1 to 0.2 millimeters outside central Delhi.
Negligible. Absolutely negligible.
And most importantly, the air quality index, the AQI, remained completely stalled in the poor to very poor range. It did not wash the pollution away.
No, it did not. And this is the critical evaluation layer you need to bring into any analysis. It exposes a fundamental flaw in using this specific tech for winter pollution, because winter skies in that region are notoriously dry.
So, if the pilot had such mixed results, a logistical win but a scientific failure, why is the government still so interested in this? Let's zoom out and look at the broader government response framework.
Well, you have to look at the other applications. The primary benefits driving government interest aren't just about urban smog. First, you have weather moderation.
Like reducing hailstorm.
Exactly. Suppressing hail that can destroy crops, or increasing winter snowfall over mountains to ensure rivers have water during the spring melt.
Ah, so water resources and agriculture are the real drivers here.
Yes. For drought-prone regions, artificial rain can boost drinking water supplies, aid irrigation, and provide critical soil moisture for rain-fed crops. That is a massive economic and security imperative.
And then, of course, the third reason is the air quality angle. The hope that it could temporarily wash away particulate matter PM 2.5 and PM 10 during severe smog episodes.
But as we just discussed, the operational constraints are brutal. You cannot make rain from clear skies. The meteorological conditions have to be absolutely perfect.
And beyond the weather constraints, we have to talk about the environmental concerns. This is a huge point for anyone evaluating this policy. We are talking about shooting heavy metals and chemical salts into the sky.
The toxicity concerns are very real. Prolonged use of chemicals like silver iodide raises serious questions about bioaccumulation in terrestrial and aquatic ecosystems.
Right. If you do this every year, does the soil become toxic? Does it poison the groundwater?
That is the scientific uncertainty. The long-term empirical evidence just isn't there yet.
Yeah.
And then you pair that with the economic viability.
Oh, the cost is staggering.
Right. Large-scale or repeated deployment is incredibly resource-intensive. It is not a sustainable daily strategy.
Which brings me to what I think is the most dangerous part of this whole policy approach, the danger of techno-solutionism.
Oh, that is a fantastic analytical keyword. Techno-solutionism.
It is this intense temptation for governments to spend millions on a flashy, artificial rain band-aid rather than doing the hard, unpopular work of actually curing the underlying disease of emissions.
Exactly. It's much easier to point to a plane in the sky than to enforce strict industrial emission cuts or overhaul urban transport.
So, understanding all these limitations, we have to ask the ultimate policy question. Where does cloud seeding actually fit into the future of governance and climate resilience? What is the way forward here?
Well, the 2025 trial represents a very specific shift in strategy. They were attempting to repurpose an agricultural drought relief technology into an emergency urban disaster response tool.
Right, using it for post-festival smog spikes.
Yes. But the administrative consensus going forward is that cloud seeding can only ever be a supplementary short-term intervention. It is not and cannot be a substitute for structural reform.
So, if you are generating recommendations for an exam or a policy brief, what are the long-term alternatives that must take precedence?
You need to focus on institutional strengthening and nature-based solutions. We're talking about expanding urban forests to act as natural carbon sinks and aggressively restoring wetlands.
Plus, sustainable urban planning. You have to have strict emission reductions at the source and build climate-resilient infrastructure. You cannot rely on a Cessna to bail you out.
Exactly. The governance pattern here is shifting from reactionary, quick-fix tech deployments toward demanding sustainable, long-term environmental capacity building.
All right, this has been an incredibly dense session. Let's wrap this up with our final revision capsule to make sure you retain the absolute highest yield information.
Let's do it.
First, the 5 must-remember facts. 1. The 3.21 crore rupee budget. 2. The Cessna 206H aircraft managed by IIT Kanpur. 3. The difference between hygroscopic, which uses salt for warm clouds, and glaciogenic, which uses silver iodide for cold ones.
4. The absolute necessity of having 50 to 60% cloud moisture for success. And 5. The fact that in October 2025, due to low moisture, there was a negligible impact on Delhi's AQI.
Perfect. Now, your 5 analytical keywords to underline in your answers: coalescence, silver iodide, interagency coordination, supplementary intervention, and nature-based solutions.
And if you have to structure a 250-word answer on this, here is your framework. Start with the context, the urban pollution and water stress crises, then break down the dimensions, meaning the technology itself and the pilot data.
Next, list the challenges. Highlight the massive costs, the reliance on pre-existing moisture, and the ecotoxicity concerns. And finally, conclude with the way forward, pairing supplementary tech with long-term structural emission cuts.
That structure right there is how you maximize your marks and show true analytical depth.
Absolutely. But before we let you go, I want to leave you with one final, slightly provocative thought, a brand new thread to ponder that ties right into national security and strategic autonomy.
Oh, I know where this is going.
If we keep pushing this tech and we eventually master the ability to control the weather, who owns the clouds?
It is a terrifying legal vacuum.
Right. Because cloud seeding doesn't magically create new water. It just forces the existing moisture in a moving storm system to drop early. So if one state or one country actively seeds clouds to pull down massive amounts of rain over their territory, are they effectively stealing that moisture from a neighboring region downwind?
You are literally taking water that was destined for someone else's agriculture. It turns weather modification into a potential geopolitical weapon.
Exactly. And in a water-stressed world, that is a conflict waiting to happen. Something to think about as you review your notes. Thanks for joining us in the War Room for this deep dive, and keep analyzing those hidden patterns. We will catch you next time.